Hello, and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. So for today's show, I'm here with Philip Johnston, who's the CEO of a really interesting company called Trackwise. Philip's agreed to come and talk to us a bit about his history and about Trackwise, a company, and the work that they're doing in and around electric vehicles and some of the key components that are going into to battery systems. So thank you for agreeing to come on the show today, Philip.
Ryan, thank you for the opportunity. Look forward to talking to you.
Brilliant. So maybe if we could start by just, if you could tell us a bit about yourself and where you are from, what made Philip?
Thank you. Yeah, so I'm an engineer by training. I did my apprenticeship with British Aerospace in Filton. So I did an engineering degree, aeronautical engineering degree with them, qualified as a mechanical engineer. Looking in there, I think it was the Telegraph jobs papers at the time, I saw how much patent attorneys were getting paid, and I thought I'd like a slice of that. So I actually went on and did a law degree, thinking that I would qualify as a patent attorney. But I did that by correspondence course while I was working, in my 20s. But I think during that I eventually wake up to realizing that I wanted to be a doer rather than an enabler. So I stayed in engineering in manufacturing. So for the first sort of 15 years post graduation, I worked in the space business for British Aerospace, and they subsequently became Matra Marconi Space, EADS, and then eventually Airbus Defence and Space, and worked the majority of time on a European satellite called Envisat. So I was a mechanical engineer, looked after the we were the prime contractor, so looked after the overall mechanical responsibility for that spacecraft, the spacecraft structure. So one of the defining moments of my life was going to be standing holding the red emergency stop button when this 8-ton satellite was sitting on the hydraulic shaker in Aztec in Nordwijk. So that was quite an interesting time as it went through its primary mode. Anyway, so 15 years in European space, and worked with some incredibly brilliant people on a very interesting project. But really, I felt that this was an environmental satellite, and we were meant to be saving the world with the satellite, and I felt that too much time and effort was really being wasted on non-productive activities. So I wanted to stay in engineering and looked around for a manufacturing business that I could add a bit of value to. So and that's how I ended up with Trackwise. So Trackwise, based in Gloucestershire. We are the business had been going about 10 years. Manufactured printed circuit boards, and they had a niche capability to make 8-foot-long printed circuit boards, which I think your listeners will probably know that most circuit boards are 8 inches in length rather than 8 foot in length.
8 foot. So 2.4 meter.
Yeah, that's right. So
what on earth do you need a 2.4 meter long circuit board for?
So these were one of the early GSM 900 base station antennas. So around the countryside and towns of the mobile phone base stations, on top of the tower is an antenna, the long grey cigar-shaped box. And in the early days, the likes of Vodafone were putting up these very large high-gain antennas, really just to maximise the coverage of early mobiles. So these were large printed antennas. So that was the reason for Trackwise developing this large format capability.
And so were you actually, because a lot of that sort of industry of like PCB production particularly is, and in fact for a long time has been in Asia, but were you guys actually doing the full sort of manufacture of that board in the UK then? Is it such a special?
So we have remained a UK manufacturer. So so this was 1999. I joined and I bought the business. I did an MBO in 2000, and so the intervening 20 years has just seen an absolutely massive change in global manufacturing, let alone UK manufacturing. So when I joined Trackwise, I think there were 5 UK antenna manufacturers, and now there's I might get in trouble with some of them, but there's basically a half, and the rest of the business has, as you say, has disappeared over to Asia. So, but my premise for buying Trackwise that if we could sell this capability to one, we should be able to sell it to others, and sure enough, we did. Funnily enough, our next customer that I acquired was in Melbourne in South Australia. So radio frequency systems who are part of the Alcatel group, and so we shipped tons and tons of product to the other side of the world, and got a Queen's Award for export. So we persevered hard, but it has remained an interesting period in manufacturing. But as I say, we're a UK manufacturer and have continued over the period.
And circuit, because we'll get to talk about other stuff in a minute, but just out of interest, as much as anything, I kind of learned the hard way that circuit boards was something that it was very easy to take for granted, but particularly as you're getting into more complex designs and layers and sort of different via technology and things like that, that actually there's an awful lot of manufacturing process technology involved in making circuit boards in any, I'm not even in any sort of volume, even in like one-off quantities, some of the incredibly complex boards. And there's a lot of like big chemical processes and big stuff needed to do that at scale. Is that that's your kind of play kit that you guys have got?
I think we'll go on to describe what we've ended up doing in making these very, very large circuits, and it's quite funny what we end up thinking is normal now, and so you are right. Sometimes you need to take a step back and think we are dealing with hazardous chemicals, and we are dealing with microns of tolerance, and really it isn't very easy to do. And yes, unfortunately, our customers do want to pay next to nothing from it. But that has been the story of the last 20 years of manufacturing, isn't it? Is complete price deflation across the board, and I think it's quite interesting now to see whether that long period of deflation in manufacturing has finally ended. So.
Well, there's a lot of contributing factors to that, and
definitely.
I think it's a really interesting time at the moment where obviously all the economies that were sort of where they were heavily subsidizing, but then maybe not necessarily competing on even terms globally, are they maturing and maybe less prone to sort of some of what was going on in the past, plus people more and more aware of the risk in long supply chains as well. But plus, I do think there's a bit of it where the process technology is now so intertwined with device performance that you sort of can't, in a lot of cases, just ship it out to some outfit that you've never met before and don't know what they can do. There's such a...
You're not going to get me to disagree with that, Ryan, so I'm possibly not the one to argue the contrary to that.
Yeah, interesting. So conventional circuit boards was the thing that you did, and very big conventional circuit boards, but then you basically ended up developing some really interesting new concepts and technology in this area, didn't you?
Yeah, so Rolls-Royce Aero Engines, a very brilliant engineer, Paul Broughton, was looking to replace the wire harness inside their aero engines with flexible printed circuit boards in order to save weight, in order to save space. And because their printed circuit boards were big, clearly these flexible printed circuit boards were going to be big, and they heard through the supply chain that Trackwise made big boards. So Rolls-Royce came to visit us, and I think it's no exaggeration to say that visit absolutely changed my life and changed the life of the business. So it's roughly 8 meters from FADEC to FADEC around the engine, and one of Rolls' requirements was that that roughly 8 meter run should be made as a single piece rather than a daisy chain of interconnected sections. And I had to think about that. We had to think about that, and came up with and patented a means of making length unlimited multi-layer printed circuits. So
on flexible substrates.
On flexible substrates, yeah. So all based on a roll to roll. So really, the last 10 years we have been developing and honing the means of making length unlimited, so length agnostic. So the longest circuit that we've made to date is 72 meters. So which was going into a
hang on. 72.
Yeah, that's right. And with about a million vias in the whole run. Yeah. So going into unfortunately, because we're producing cutting edge technology, quite often this becomes part of the secret sauce of our customers, and so they. I have to be careful that we don't name names, but anyway, so it's for a nuclear fusion application, and
I'd say whatever it is probably big enough to see from space, because it's a big circuit board.
That's not actually the case, but anyway, so I think that our base. So a printed circuit board is in general limited by the size of the manufacturing equipment used to manufacture it. So I don't know the precise statistics, but 99% of the world's manufacturers can make only up to 2 foot in length, so 600 millimeters. So we have come up with a means of making length unlimited, length agnostic, so all done on roll-to-roll manufacturing, and that is what we have patented and then invested in and perfected and are rolling out in our 2 facilities now in Gloucestershire.
So maybe actually, because I know I talked to people involved in the flexible circuit industry previously. So I think we have some mutual friends at Centre for Process Industries, CPI, up in the Northeast. And if I'm honest, the first time I heard about this a few years ago, I just couldn't even get my head around what it even was. So I think I was like, yeah, that's very interesting, and then put it in the too difficult to compute box. But having been to CPI fairly recently and seen some of the kit that they've got, it's like, I had a big eureka moment. But I think it's quite hard. Well, I don't know, maybe it's just, perhaps just me being a bit of a Dumbo, but quite hard to sort of visualize what someone actually means when they say a flexible circuit. So give us the sort of, what is it?
So we have branded this technology improved harness technology. So fundamentally, a flexible printed circuit was developed in the middle of the last century in order to replace wire harness. So instead of having a bundle of individual wires which you strip from a reel, wrap together, put a connector on the ends, you're using printed circuit technology to etch from copper the individual circuits that replicate that wire. And as a result of replacing wire by a flexible printed circuit, so individual strands of copper, etched copper, replacing individual wires, you can save 60-70% of weight as well as a load of space. So the weight and space saving is really the key opportunity. And at the moment, most airplanes, most airplanes, most cars are wired using fundamentally 100-year-old technology. And our proposition to the market using improved harness technology is that there's a better way. And particularly for electrification, both automotive and particularly for aerospace electrification, where the energy source is limited, to move mass around, mass is energy, is cost, is carbon. And so really that is where the weight, particularly the weight saving agenda, is so important. So instead of having a bundle of wires, individual wires, we're etching circuits of any length to form a wire harness replacement.
So you take a polymer material?
Blank sheet, a copper-clad laminate, as we call it. So typically a polymer, polyamide or some sort of polymer covered in copper, or sometimes nickel, or sometimes other metals, and using a digital imaging process to define what circuit we want to lead on the circuit, define the imaging step, and then etch it to leave the individual copper traces. And so that can be done with very, very high degree of accuracy. I mean, copper etching is going back to your earlier point, is a very precise, very repeatable manufacturing process. And thanks to Trackwise's innovation, can be done on any length.
Well, rather than, because normally you sort of like prepare a particular area and do a sort of an exposure, and then move on to the next area, then do an exposure bit. You're talking about much more sort of continuous. You are talking about
it is a continuous process. Yeah. So we have worked very closely with our equipment suppliers to help us develop a means of making this length unlimited.
And then we'll come back to the sort of the problem with harnesses and things in a second, because one of my sort of topics from my history. But you've also got people doing clever things, and this is what the CPI guys had, where they, as well as that sort of conventional circuit production, you're also able to add features as well, aren't you? Sort of print and put stuff onto that on the reel-to-reel process.
Yeah, so CPI are doing the slightly different process, so Trackwise is etching circuits, which is subtractive, and then other people are doing additive. So and slightly different ends of the same market. So CPI are doing things like RFID tags in large volumes, and but using very similar technology. So what we are doing also is, as I described, we are replacing a passive wire harness with a passive flexible printed circuit, which can save 60-70% of weight. However, we are replacing with a flexible printed circuit, and onto that you can place any surface mount component that you need, and that has the opportunity to turn a passive interconnect actually into an active interconnect. So you can put local sensing, local signal conditioning, replace a passive interconnect actually by an active interconnect. So slightly different approach than CPI taking, or the additive approach, but very similar.
Yeah, and I guess like sort of hybridizing the two is very possible, and
definitely.
And it is because you made the point earlier that the technology in a conventional wiring harness is effectively really old hat, and I think a lot of people would be surprised to know that even in really, really high volume applications, handling wires is really difficult. So trying to sort of terminate wires and put connectors and terminal pins and stuff onto them is really tricky, and automating that process, doing it fully by machine and then bundling it into a harness actually is really, really difficult, because wires are floppy and quite hard to control. So like semi-automated, but there's a lot of labor goes into building wiring harnesses, even in very high volume manufactured products, and then
it is a labor intensive manufacturing process, and whereas particularly the roll-to-roll flex PCB manufacture is a very machine intensive manufacturing process, which is hopefully why we can make it pay in the UK.
Yeah, because a lot of the wiring harness stuff has ended up being outsourced to like North Africa or quite low labor cost countries, but then you're back to having that supply chain risk and those sort of things creeping back into the process. And the other thing with in wiring harnesses, like the most common sort of failure is a failure around the connection between the wiring harness and the thing that it's connecting to. So terminal pin failures, incorrect application of pins, and sort of and even incorrect insertion of connectors. I mean, that's a surprising, even with all the sort of interlock systems that you get these days on connection systems. It's very, very, very difficult bit of engineering, hard to get repeatable, lots of cost in connectors and sort of that kind of thing. So you can basically completely rethink the way that you harness out anything with your technology. Is that?
Yeah, I mean, we are. I mean, believe me, it's been difficult enough to change the way an aeroplane is wired without changing the way that it's connectorized as well. But the initial starting point is that we will reuse existing aerospace connectors, but with another company, we are in the process of developing a much more flex specific connector. So it is a you're right that it is a problematic area, an expensive area.
And then so obviously the podcast we talk about electric vehicles and autonomous vehicles, and there's one area in particular on electric vehicles that you've been looking at, if I'm right, is
Yeah, so battery modules, battery packs are, we think, an absolutely ideal use case for flex PCBs. So in any battery module or indeed battery pack, you've got many cell termination positions which are in highly repeatable, highly defined, highly repeatable locations. So like you said, a wire harness is floppy. If you wanted to connect to all those different cell locations using wire, it would be a very problematic manufacturing exercise. So whereas a flex printed circuit you can just place on directly on top of on the cell stack, weld them into place, and indeed, because of the nature of a flex PCB, it's very amenable to be handled by robotic handling. So again, I think in the context of or in the branding of improved harness technology, the improvement that Flex is offering, apart from the weight and space saving, is manufacturability. So yeah, and then I think if you then extend new technologies going in cell to pack or even cell to vehicle, where the modules become pack level or vehicle level, really the interconnect becomes even larger, and that really plays into Trackwise capability, where we are quite happy to provide 2 meter long circuits for cell to pack applications, and I'm very interested and very excited about that as a coming technology.
Because in my past experience of developing battery packs and systems, actually the wiring harness design inside the pack was normally very complex and actually because you had a sort of double problem of, if you had a harness issue, obviously you had an issue with the things you were trying to measure. So you typically in a pack have heavy bus bars for moving the current around, but then quite an extensive wiring harness for the sort of instrumentation for the battery management system to measure temperatures and cell voltages and such like. So cables going everywhere, and obviously if the harness failed, you lost the signals that it was measuring, but then you also ended up with a conductor potentially floating around inside the pack, which is not ideal. So really safety critical on pack design. So it must be being able to take the harness away and move to a much more controllable system, like a flexible printed circuit, must make it an awful lot easier to integrate the harness into the battery pack.
That we believe is the use case. Obviously, instead of having 101 wires, you've got a single flex PCB, and as I say, that is very, very precisely geometrically controlled and very, very, very repeatable. So really, from manufacturability, particularly when you're laser welding and things, are very, very, very tightly defined locations. We think it's an ideal use case. And really, that's from a sort of a technological perspective. The other thing is, again, from a UK manufacturing perspective, I think the reason that there's a significant drive to build gigafactories in the UK is that cells and battery modules, battery packs are very expensive and problematic to ship around the world. And so really, cells and modules and packs need to be built close to vehicle build, and so really that is the proposition for Trackwise, is that we're going to provide a world-class capability for cell interconnects close to the point of manufacturing. Certainly that's what we're developing, amongst many other things.
And is it? I mean, genuine question, but because you've got the high current carrying conductors, so typically bus bars, and you see them sometimes laminated structure. Are you sort of integrating with bus bars and kind of that sort of side of things, or is the flex circuit separate, or how's that being done?
So we are making both high voltage and low voltage circuits, but I think so. But I think probably the more, and that slightly depends on the cell format, but I think the I was about to say the universal use case, but the more general use case is for the low voltage rather than the high voltage. But certainly we are making high voltage circuits, so for primary power collection. So again, I think people are quite surprised about that, but
I actually, to be honest, I mean, I asked the question, but I'd half assumed that maybe weren't able to do the high voltage current carrying with a flex. So
no, you are. So wow. For relatively bit thicker copper, but
because I mean a lot of packs use this sort of, as I mentioned before, laminated structure. So that would be similar polyamide type material, and then with the sort of pressed copper. Actually, tin plated or plated bus bars contained inside, and then a sheet. So lay down a sheet, lay down the sort of pressed components, lay down another sheet, and you end up with a sort of single component that's actually got quite a bit going on inside it, but it's a single.
That's fundamentally correct, Ryan. Yes. So, and again, all in very precisely controlled and repeatable geometries, such that they're amenable for welding to the precisely defined, weld positions.
Wow. And it's in terms of deploying flexible circuits and or improved. It's funny because in the automotive world, I think from my recollection, I mean, I said before, it was something that I just sort of like, when I first heard about it, I thought, I don't really get that. And then no one's really done much around harnessing innovation, other than there was a Tesla patent a couple of years ago, which they were looking quite, because the other, actually, having said wiring harness, build is manual. Actually, if you go to a car plant, the harness fit into the vehicle or into the subsystem, like onto an engine or into the battery system, tends to be manual as well, because you've got this big floppy wiring harness. And it's quite funny often watching the guy, a particular plant, going, basically lying on his back like a sort of maroon turtle with his special shoes on that were carrying bits of the harness, and, kind of stuffing this harness into the vehicle. And you sort of look at it and you think, wow, that doesn't look like a sort of modern production process, but they're very, very difficult things to handle. So Tesla came up with a concept of doing like basically a harness as a sort of rigid mechanical component, where they had sort of rigid bus bars and then other bits. But other than that, you don't really see people innovating much on harnesses. Do you think that's is that something that you think is going to change in the future?
Well, I haven't seen. I obviously am aware of the Tesla patent, and I haven't seen that it's being implemented, or haven't been aware that it has been implemented. But that was music to my ears, because that's fundamentally a slightly different way of the same concept that we're offering. So I think if I optimistically project myself forward 10 years, I think it's highly unlikely that flex PCBs will replace even the bulk of wiring within the vehicle. But I think if you look at a different vehicle architecture, the zonal architecture that they're talking about, it may well be that the backbone between the individual zones would be or could be or should be done by flex. As an improvement, but I think the local geometry to the individual, switches and doors and window controls are probably going to have to still be affected by wire. But at the moment, there's only one technology available to the designer, which is wire. But our intent, our mission is to allow them to have a choice on the drop-down menu for the design options.
Okay, cool. It's really interesting. And then in the battery system, are you seeing much uptake of that in terms of people starting to look at using flex to build in?
So we have a innovative and strong first customer who remains nameless, but we're in at their request. But we're in the process of building a fairly large factory just south of here to deliver that, and are in extensive discussions with other OEMs and tier ones about the rest of the capacity. There was a very interesting analysis put out yesterday, the battery report. I don't know whether you've seen that yet, but a very interesting read. And one stat stood out for me, that the European battery manufacturing is forecast to grow from 57 gigawatts in 2020 to 480 gigawatts in 2025. So that's an 8-fold increase in battery manufacturing in Europe over just a 5-year period. And I would be absolutely amazed if the second half of our facility down the road is not used very quickly, because every single one of those cells has to be interconnected and controlled, as you mentioned, from a thermal and voltage perspective. So
I think I know who. It's funny. Before Christmas,
don't mention the name, or I'll have to redact it.
No, I won't. Don't worry. But I did. What I was going to say is I saw a story. Actually, it was a sort of technical white paper from a certain company, and it was around this topic. And I logged it as, that's really interesting. And then I went back to try and find it a week or so later, and it had vanished, and has had any other trace of it being mentioned. I thought, someone in the PR department there obviously got a bit carried away and put out something they shouldn't have. It was quite to the point where I actually thought I was going mad.
It's very frustrating when you find something and then can't re-find it. So
yeah. So. They're
a very exciting business, and a very exciting UK business, more to the point, and we're delighted to be part of it. And the battery is such a key part of any electric vehicle, obviously, and Trackwise is making some pretty key components to go into that. So we're very excited about that. But as I say, we're at such a epoch. Such a change point in the industry, in the automotive industry, and as reflected by that forecast 8-fold demand increase over the next 5 years.
And actually to have something different on the front of that, so you're not just battling it out against the lowest cost labour, harness assembly people is a really exciting place to be, I'm sure. So difficult questions then. What are the drawbacks? Is it like mega expensive tooling? Is it higher cost? Like what? There's got to be some downsides to this technology.
Come
on.
I would have to say none, but so I think for different applications, the drawbacks are different. So one of the things, I told you that we started from aerospace, and we've got quite a bit of a lot of activity going on the aerospace, particularly the more all electric aviation perspective, and the repairability is not latched upon, but is considered to be a bit of a drawback. So a bundle of wires, in theory, if you damage a wire, you can splice in another one. Whereas a flexible printed circuit, if you've got a bundle of traces, or a string of traces with an individual flex PCB, if you damage it, it's not really amenable to such repair. So, and the other thing is that you mentioned the floppy nature of wire. So the advantage of that is that it can bend in all directions, whereas a flexible printed circuit board doesn't have the it bends in pitch up and down, but when bends side to side. So when I've been having discussions with particularly aerospace customers, things have gone well. They metaphorically hand me a wire design and say, tell us what that would look like in flex. And so part of me thinks, that's great, they're interested, and part of me thinks, if they designed it in flex, it wouldn't look like this. So and just going back to the battery point, that is why batteries are such a good use case. They're flat rectangular blocks, very good geometrical use cases for flex PCBs, and that's really why I think that rather than necessarily the body in white or the doors or whatever of automotive, the battery is an absolutely ideal use case for that. So.
Right. Okay. And interesting. One thing that springs to my mind as a question is is there a limitation in terms of how many layers you can build up? Is it always one layer?
There is. So I mentioned our patent is around multilayers. So typically, again, for aerospace or space applications, you're wanting shielded wires, and therefore you're typically wanting a 4-layer board, so which is 2 conductor layers with 2 shields on the outside. So and if you think of a wire harness, you're never going to want to go much more than 4 or 6 layers, really. If you just think about what a wire harness looks like. So occasionally you can have a shielded wire with an overbraid, and that's effectively a 6 layer. So it isn't characterized by very high wire counts, by very high layer count.
Yeah. So I guess the advantage. So compared to a sort of conventional PCB, where you can get lots of layers, but then it's rigid and you've got components on it, and it's a functional circuit, compared to a wiring harness where you've got a bundle of cables. You can print multiple tracks on a single layer here, so you could have actually lots of stuff going on one layer in a sort of different way.
Yeah. And that's really where because you're not reeling off individual wires from a reel and putting them all together, we're able to package it in a much more efficient manner, and that the space saving is very, very significant, and that is very interesting. Again, in aerospace, where a modern system in general, regardless of what industry you're talking about, typically people want a greater functionality in a smaller form factor. And at lower cost, but that greater functionality in a smaller form factor is definitely is one of the macro trends that is playing in our favour on them. So,
with the wiring harness, there's often like issues, reliability issues. One one of my favorite, really bizarre failure modes that you say. Favorite failure mode? Yes, I did just say that. When you get on a conventional multi-strand wire that isn't fully filled, you can get this sort of capillary effect where liquids are drawn up the wire. And actually, really interestingly, if one end of it is attached to a high power device like an EDU or an electronics module that's getting hot, the sort of heating and cooling on one end of it can actually act a bit like a pump and kind of draw fluids through seals and stuff like this, and you end up with, you can sometimes end up with really random problems with the wiring harness sort of rotting out. From an environmental point of view, how can you deal with that sort of thing?
We can do, and again, that is going back to the disadvantage of you not being, or the perceived disadvantage that we're not able to repair it. The reason we're not able to repair it is that it's a single integrated item rather than an assembly of individual components, and therefore that integrated item means that there are less failure modes. That there isn't this channel for this wicking, etc. But
yeah. And I think that'd be pretty important. You can imagine some very high integrity applications where actually that would be a major advantage because of the issues around harnesses and that sort of problem. So when you're making this the structure up, you can bring the different layers together. Probably last question for me before I asked you a bit about the future, but how do you bring it out? So how do you go about terminating it? You mentioned the more sort of flex-centric connector system, but how do you join it into stuff? Basically, how's that work?
So I think, as I mentioned earlier, so particularly on the aerospace side, we want to reuse existing connectors, and because this is not new technology, a flex printed circuit has been around for such a long time. There are flexible printed circuit board terminations for just about all aerospace connectors. So it's a little bit more problematic in automotive, but certainly for aerospace, there are we can put a connector directly onto the FPC through plated holes or by termination. But equally, we can do we can terminate in wires, so do a flex to wire transition, and so then once you've transitioned to wire, you can then go into any connector or any geometry. So quite often we are using a sort of a hybrid construction. Like as I said, for the car, you have the main harness down the front of the body in white in flex, but then branching out into wires for breakouts and routing to individual terminations elsewhere. So that flex to wire transition is quite an important technology.
Okay, yeah, well, really interesting. So that's been a fascinating discussion about the sort of
Thank you.
The company and the technology, and I've it's really helped me to get a better sort of feel for flex and particularly how you might use that in a battery system. So what's got you what are you excited about for the next year and the future? What things are you most looking forward to?
Well, as I said, we haven't touched on the fact that we're an AIM-listed business. So we floated in 2018 and have done a number of raises since. So that has largely been to fund the innovation and the expansion of our capabilities. So we're in the process of equipping a new facility down here in Stonehouse in Gloucestershire, and I'm very excited to see that up and running in the first quarter of this year in full production about in the middle of the year. So that is going to be a major growth story for the business and a major milestone for the business, and really that the ability to show to our investors where their money has gone, other stakeholders, other customers, showing we have an internal mantra, quantity, quality, qualified. So when we can demonstrate to ourselves, to our investors, to prospective customers that we can manufacture, boards at rate to the requisite quality, and these are being used in anger in live vehicles, then I think that's going to be very powerful. So that is probably my single excitement about 2022. But equally, as I mentioned, we're really only occupying half of that facility, and my real mission is to get the next OEM, the next tier one, to understand that they're going to need that capacity and to sell that going forward. So, yeah, and we haven't even mentioned things like medical catheters that we're doing as well. So the same technology is very applicable for medical catheters and things. So we've got a huge amount going on across multiple different channels.
Oh wow, a catheter.
That's maybe a separate discussion, but I think
makes my hair stand up just thinking about it.
the real opportunity, in my opinion, is the battery space. It's as we've just described. So very, very interesting time to be in business. I think it's not often in the life of an SME, and we are still a small business, that you get a globally innovative technology, and I'm very interested and exciting to see how far we can go with it in our three verticals: EV, medical, and aerospace.
Well, I mean, even the EV, that actually, we often talk about the electrification of everything, because you've got an awful lot of things like warehouse robotics, which are effectively EVs moving around, mobile robotics platforms, which have battery packs and more complex wiring systems and batteries and stuff, and electrification in aerospace, you mentioned already, electrification in automotive. There's such a lot going on around electrification in all sorts of sectors. That has a lot of cross-pollination, like a lot of crossover opportunities and things like that. So it's brilliant. So it's been absolutely fantastic to talk to you, Philip. Really pleased that we managed to get the time to do this. I'll put loads of links and things down in the show notes. So hopefully that next OEM might have been listening, and if they go to the show notes, they'll be able to find out how to get in touch with you. But that's been great. Thanks. Thank you very much for taking the time.
Thanks for the opportunity. Nice to speak to you, Ryan. Yeah.
Brilliant.
Bye for now then. Thank you.